Section 7.3 of your textbook covers the elimination method for solving systems of equations. Remember that a system of equations is a set of two or more equations that are to be solved simultaneously. And a solution of the system must also be a solution of every equation in the system. We've previously discussed the graphing and substitution methods for solving systems. The elimination method, like the substitution method, is an algebraic process that does not require drawing a graph. To solve a system of two linear equations by elimination, we'll use 5 steps. First, rewrite both equations in standard form ax plus by equals c. Second, if necessary, multiply one or both equations by a constant so that terms containing the same variable have opposite coefficients. Third, add the two equations to eliminate one variable. Fourth, solve the resulting equation to find the value of one variable. And fifth, substitute to find the value of the other variable. Our first example is shown on the slide. 2x minus 3y equals 17, we'll call that equation 1, and 4x plus 3y equals 7, we'll call that equation 2. Notice that both equations in this system are already written in ax plus by equals c form, and also notice that the y terms in these equations have opposite coefficients of -3 and +3. So we can move right to step 3 of the elimination process and add the two equations in order to eliminate y. On the left-hand side, we add 2x plus 4x, and we have 6x, and then we add -3y and +3y to obtain 0. On the right-hand side, 17 plus 7 is 24. Now it's important to note that this step of adding these two equations together is valid because of the addition property of equality. Equation 2 is saying that the expression 4x plus 3y is equivalent to the number 7. So we can add that expression on the left-hand side of equation 1 while adding the number 7 on the right-hand side of equation number 1. Now we proceed to solve for x by dividing by 6 on both sides, and we have x equals 4. Finally, we can substitute back into either of our two equations to find the value of y. Let's use equation 2. So we have 4 times 4 plus 3y equals 7, or 16 plus 3y equals 7. Subtracting 16 on both sides, we obtain 3y equals -9, and dividing both sides by 3, we obtain y equals -3. This means the solution of our system is the ordered pair 4, -3. And if we were to graph these two equations, we would see lines intersecting at that point. Let's look at two more examples that are slightly more complicated. In problem 1, 3x minus 5y equals 16 is equation number 1, and 6x plus 2y equals 8 is equation number 2. Both equations are written in the form ax plus by equals c. However, neither the x nor the y terms have opposite coefficients. So we need to perform the second step of the elimination process, which is to multiply one or both equations by a constant. In this case, the easiest way to obtain opposite coefficients would be to take equation number 1 and multiply both sides by -2. So we would have -6x in equation 1 compared to 6x in equation 2. So let's rewrite equation number 1 as -6x plus 10y equals -32. Now we can proceed by adding these two equations together. 6x plus -6x is 0. Since those terms cancel out, x is eliminated from our system. 2y plus 10y is 12y. And then on the right-hand side, 8 plus -32 is -24. Thus we see that y equals -2, and we can substitute back to find the value of x. Let's use equation 2. So we have 6x plus 2 times -2 equals 8, or 6x minus 4 equals 8. If we add 4 to both sides, we have 6x equals 12, and if we divide by 6 on both sides, we have x equals 2. Thus, the solution of the system is the ordered pair 2, negative 2. Let's look at system number 2. Equation 1 is 2x plus 3y equals 13. Equation 2 is 5x plus 4y equals 15. Now in this case, there's no whole number that we could multiply by equation 1 to obtain an opposite coefficient from equation 2. So we'll actually multiply both equations by constants. Note that if we multiply equation number 1 by negative 5 and equation number 2 by 2, our x terms would be negative 10x and positive 10x. So we'd be able to eliminate them by the adding process. So let's perform the multiplication and rewrite our system. Equation number 1 now looks like this. Negative 10x minus 15y equals negative 65. Equation number 2, positive 10x plus 8y equals 30. Now we can add the two equations together to eliminate x, and we have negative 7y equals negative 35. Dividing both sides by negative 7 gives us the y value of 5. And now we can substitute back in to either of our two equations to find x. Let's use equation number 1. 2x plus 3 times 5 equals 13. And now solving for x, we see that x equals negative 1, so our solution is the ordered pair negative 1, 5. Now in solving this system, we chose to multiply the equations by negative 5 and 2 in order to obtain opposite coefficients on our x terms. It's also equally possible and valid to obtain opposite coefficients on the y terms. We could, for example, multiply equation number 1 by negative 4 to obtain negative 12y, and equation number 2 by 3 to obtain 12y. And if we solve the system in this way, we would eliminate the y terms first, solve for x, and then go back and find the value of y, and we would obtain the same answer that we found using this first method. Let's do two final examples to see what happens when the elimination method is used to solve systems that have either no solutions or infinite solutions. In problem number 3, equation 1 is 2y minus 4 equals negative 3x, and equation 2 is 6x plus 4y equals 8. Notice that equation number 1 is not written in our standard form, so let's add 3x to both sides, and let's also add 4 to both sides. If we do this, equation 1 will now be written as 3x plus 2y equals 4. Now that both equations are in standard form, we look for opposite coefficients. Since we don't see any, we need to multiply one of our equations, or both, by a constant. In this case, the simplest way to obtain opposite coefficients would be to multiply equation number 1 by negative 2. So now for equation number 1, we have negative 6x minus 4y equals negative 8. Recopying equation 2 from above, we have 6x plus 4y equals 8. When we add these two equations together, notice that both the x and y terms cancel out on the left-hand side, so we have 0. And on the right-hand side, negative 8 plus 8 is also 0. We've seen that if we obtain an equation that is always true like this, this means that we actually have two equivalent equations in our system, and therefore there are infinite solutions. This means that if we were to graph these two equations, we would see that they produce the same line, and all points on that line are solutions of the system. Let's move to system number 4. Equation 1 is 6y equals 4x minus 9. Equation 2 is 2x minus 3y equals 5. Notice that, once again, our first equation is not written in standard form, but we can obtain standard form by subtracting 4x on both sides. So equation 1 now reads negative 4x plus 6y equals negative 9. We don't have opposite coefficients, but we could obtain opposite coefficients by multiplying equation 2 by 2 on both sides. So now equation 2 is 4x minus 6y equals 10. Adding the two equations together, we see that the x terms and the y terms on the left-hand side cancel out. So we have 0. But on the right-hand side, negative 9 plus 10 is 1. The equation 0 plus 1 is false. This means there are no values of x and y that can satisfy the system. We say that this system has no solutions. And if we were to draw a graph of these two equations, we would see that they produce parallel lines.